Let's talk about Google's Willow chip, a quantum computer.
What if I told you that a computer chip smaller than your thumbnail just did something that would take the most powerful machines on Earth longer than the entire age of the universe to accomplish? Not a few years, not a million years, longer than the universe has existed, by a factor so large the number doesn't even have a common name. And it did it in under 5 minutes. That is not a metaphor. That is not science fiction. That is what Google's Willow quantum chip actually did. And ever since the announcement landed, physicists, computer scientists, and philosophers have been asking a question that sounds like it belongs in a Hollywood screenplay. Did this chip just reach into parallel universes to find the answer? Today we are going to dig into that question seriously, because it deserves a serious answer. We are going to talk about what quantum computing actually is, what Willow specifically achieved, why some of the world's most respected physicists believe quantum computers might be drawing computational power from alternate realities, and why others think that idea, however fascinating, might be getting ahead of the evidence. By the end of this video, you will have a genuine understanding of one of the most extraordinary technological moments in human history. Let's get into it. To understand what makes Willow remarkable, you first need to understand what makes quantum computing fundamentally different from everything that came before it. Every computer you have ever used, your laptop, your phone, the servers that run the internet, operates on the same basic principle. Information is stored and processed as bits, and each bit has exactly one value at any given moment, either 0 or a 1. Everything your computer does, every email, every video, every calculation, is ultimately a long sequence of zeros, and ones being shuffled around at tremendous speed. Classical computers are extraordinarily good at this, but they are still, at a fundamental level, doing one thing at a time, or at best a limited number of things simultaneously through parallel processing. Quantum computers operate on an entirely different principle, one rooted in the genuinely strange behavior of matter at the subatomic level. Instead of bits, quantum computers use qubits, and qubits behave according to the rules of quantum mechanics, which are unlike the rules governing anything in our everyday experience. The first key property is called superposition. A classical bit must be either 0 or 1. A qubit, however, can exist in a state that is effectively both 0 and 1 simultaneously, until it is measured. This is not a metaphor or an approximation. It is a literal description of how subatomic particles behave, and it has been experimentally confirmed countless times. The practical consequence is that a quantum computer with multiple qubits can, in a meaningful sense, explore an enormous number of possible states at the same time. The second key property is entanglement. When two qubits are entangled, their states become correlated in a way that has no classical equivalent. Measuring one qubit instantly tells you something about the other, regardless of the physical distance between them. Albert Einstein famously called this spooky action at a distance, and spent years trying to disprove it. He was wrong. Entanglement is real. It is experimentally verified, and it allows quantum computers to coordinate information across qubits in ways that have no parallel in classical computing. Put these two properties together, and you begin to see why quantum computers represent something genuinely new. They are not simply faster classical computers. They are a different kind of computational machine, one that processes information in a way that exploits the deep structure of physical reality itself. Google's Willow chip contains 105 qubits. That number matters enormously, because in quantum computing, adding qubits does not simply add processing power. It multiplies it. Each additional qubit doubles the number of states the system can represent simultaneously. Going from 50 to 105 qubits does not roughly double Willow's capability over its predecessor. It makes it billions of times more powerful. The specific task Willow was given is called a random circuit sampling benchmark. Without getting too deep into the technical details, the challenge involves generating outputs based on an extraordinarily complex set of entangled quantum states, patterns so intricate and interconnected that simulating them on a classical computer requires tracking an almost incomprehensibly large number of variables simultaneously. It is a problem specifically designed to be easy for quantum computers and extraordinarily hard for classical ones, which makes an ideal test of genuine quantum advantage. Willow completed this task in under 5 minutes. According to Google's research team, the same calculation would take the fastest classical supercomputer currently in existence approximately 10 septillion years. To put that number in perspective, 10 septillion years is written as a 1 followed by 25 zeros. The current age of the universe is approximately 14 billion years, a number that doesn't even begin to appear on the same scale. This achievement builds on Google's earlier claim of quantum supremacy in 2019, when a 53-qubit processor completed a calculation in 200 seconds that Google estimated would take classical computers 10,000 years. That earlier claim was challenged by IBM, which argued that with the right approach, a classical computer could simulate the same task in a matter of days. Willow's margin is so vastly larger that similar objections simply do not apply. The gap between what Willow did and what any classical machine could do is not a matter of clever programming or clever hardware. It is categorical. Equally significant is Willow's approach to error correction. Quantum systems are phenomenally fragile. Qubits lose their quantum states through a process called decoherence. Any interaction with the surrounding environment, even a stray vibration or a tiny temperature fluctuation, can cause a qubit to collapse prematurely. For years, this fragility was the central obstacle to building practical quantum computers. More qubits meant more errors, and more errors meant unreliable results. Willow incorporates a new error correction architecture in which adding more qubits actually reduces the error rate rather than increasing it. That is a fundamental reversal of what was previously the dominant challenge, and it represents arguably the most important engineering breakthrough in the announcement. Now we arrive at the part of the story that has captured the imagination of people far beyond the physics community. Where exactly is Willow doing its calculations? The question sounds philosophical, but it has a serious scientific context. The answer depends entirely on which interpretation of quantum mechanics you accept, and this is an area of genuine, unresolved debate among physicists. The most widely taught interpretation is called the Copenhagen interpretation. Under this view, a qubit in superposition does not actually exist in multiple states simultaneously in any physical sense. The superposition is a mathematical description of our uncertainty about the qubit state. When we measure it, the wave function collapses, and we get a definite answer. Under Copenhagen, a quantum computer is an extraordinarily clever probability machine, but it is not doing anything that requires alternate realities to explain. The competing interpretation, proposed by physicist Hugh Everett in 1957 and developed extensively by David Deutsch, is called a many-worlds interpretation. Under this view, the wave function never collapses. Every time a quantum event could go one way or another, the universe literally branches. Both outcomes happen, but in separate, non-communicating branches of reality. What we experience as a measurement result is simply us and our version of the universe, following one branch. David Deutsch, who is one of the founders of quantum computing as a theoretical discipline, has argued forcefully that the many worlds interpretation is not just philosophically interesting, but is the only coherent explanation for why quantum computers work. In his view, when a quantum computer performs a calculation by exploring many possibilities simultaneously, those possibilities are literally being processed in parallel universes. The answer we receive is a result of computation distributed across a vast number of branching realities, with the interference between those branches producing the correct result in our world. If Deutsch is right, then Willow is not just a clever machine. It is a device that is genuinely tapping into the computational resources of a near-infinite number of parallel realities. The reason it can solve in 5 minutes what would take a classical computer longer than the age of the universe is not simply clever engineering. It is because it is, in a very real sense, not computing alone. This is genuinely exciting to think about, but intellectual honesty requires engaging seriously with the counterarguments, and there are good ones. The most fundamental objection is that the many worlds interpretation, while internally consistent, is not the only interpretation consistent with experimental data. The Copenhagen interpretation, the pilot wave theory proposed by David Bohm, and several other frameworks all make identical predictions for every experiment we have been able to conduct. The question of which interpretation is correct is not currently decidable by experiment. It remains a philosophical disagreement about the nature of reality, not a settled scientific question. Critics, including physicist Sabine Hassenfelder, have also pointed out that Willow's benchmark task, while genuinely impressive,